Right, so in question, we have air flowing a stationary plate, and that represents the direction. So it's the last choice that's correct since there's not a physical boundary preventing that flow in the direction or in the y direction, y equals. Question two, we have two cases of flow over a flat plate, but you can see the boundary layer is thinner in the first case and it develops more. So that would be the case for a fluid that has a very viscosity. And looking at that Reynolds number, we can see that if the viscosity is low, that Reynolds is high. So the fluid in case one is less viscous, so it's going to have viscosity and a higher Reynolds. Question is just a matter of picking correct. That word non-dimensional, the fact that doesn't have any use. So the second answer is correct. Question four, so this refers to a fluid flowing over the surface. Um, Remember that the fluid that's in direct contact with the plate has zero velocity, and so if steady state conditions are reached, then the stationary molecules have also reached thermal that surface. So the correct option is option. Question five. So this is a question that you really would have been able to answer. This is Newton's law of and the thing that might have caused you pause would be that bar over h. But now we know that there's a difference between an average values, and so we kind of want to be specific about that when we talk about convection problems in here. So option D is going to give us the correct units for that convection. Question six, this is very similar to question five. And again, we have reference to the average convection transfer. Both A and D are the correct forms for question seven. So the critical value of that Reynolds number for flow over a flat plate is 500,000. Um, Remember that indicates where we say that transition from laminar to flow. There's definitely a range of values here, and it's dependent on surface roughness and the free condition. So we can say that really all we could say is that general place where that transition occurs is at that critical X, that critical location X designated by that reference number. All right, question eight. This asks us to look at how the velocity boundary layer affects heat transfer. So we know that turbulence increases mixing, that increases heat. But if you want to prove that to yourself, you can look at the equation, dimensionless heat transfer equation sheet. So that Nusselt number, given Reynolds number, calculate the Nusselt number, turbulent flow, and laminar flow, and you should see that for turbulent, that Nusselt number is going to be bigger. Question nine asks us to relate the velocity boundary layer thickness to the thermal boundary layer thickness. The Prandtl number is what relates the momentum, viscous effects to the thermal effects. And if that Prandtl number is greater than 1, that means that the viscous effects are greater than thermal effects, and so that velocity boundary layer is bigger than the boundary layer. So if the Prandtl number increases, the ratio of that velocity boundary layer to thermal boundary layer thickness will also increase. This is just a definition question. Remember, we do have kinematic and dynamic viscosity terms, and so you put that Prandtl number in terms of both of those terms. So both A and B are correct here. This is another definition question. Note that the V in this is the same as U infinity, the stream velocity. So just looking at your see that the correct equation. Question 12. So here we're looking at the temperature distribution, the fluid above the heated plate. Um, so actually, this is not a heated plate. This is just a plate at a different temperature than the T infinity. So TS and T infinity are different, right? You've got a temperature. So if I look at figure 6.2 in the book, so this is for a thermal boundary layer, and you can see that none of these have the same shape. And so as I was mentioning before about the heated plate, so figure 6.2, that's the case where we have this heated plate. So you can see that the temperature, as you get closer to that plate, it's approaching the surface temperature of the plate. Um, but you could see in really all of these A, B, C, D, and E that your surface temperature on that x-axis, your surface temperature is less than T infinity. So you're looking at the case of a plate that's cooling the. Um, so probably not A, probably not B, probably C, D, or E. And it's the answer is C. So while both figures, if you look at, I mean, it's yeah, C is this linear relationship, which is definitely not correct. But um, yeah, so if you look at D and E, and why is it not D or versus E? So remember, I think it was, gosh, I think it was maybe question or problem 4 on this list said that the molecules that are right in contact with that plate, if you steady state conditions, the molecules that are right in contact with that plate, they're not moving, so they will thermally um, the plate, and so the fluid temperature really does go from S to infinity. So it's the answer right there. All right, so question 13. We got two scenarios here. We got fluid flowing over a plate of length 2L, or case 2, which is or arrangement 2, got fluid flowing over two plates at the same time, and each of these is just half of that length of 2L, or just a length of L. So the area in total is the same, but in the second case, we're not really giving that the fluid in the boundary layer as much length to heat up if you've got a heated plate. So for arrangement 1, we have this smaller delta T, delta Y, so you have a lower rate, and so the answer is A. Got We're looking at the relationship between Reynolds number and the Nusselt number in laminar flow. So if we look at the average um, Nusselt, yeah, if we look at the average Nusselt number, and it'll be the same if we look at the local Nusselt number as well, since we're taking the square root of the Reynolds number in both cases. Um, See that if we doubled that Reynolds number, that Nusselt number wouldn't increase by a factor of 2, but it would increase by 1 factor of 1. So the correct answer is D. 15. So this has laminar flow over a flat plate, and we want to look at the trend of the local convective heat H with position. And so we saw in the problem that we just did, question 14, how that heat transfer rate is going to decrease as we move the length of the plate, since our delta y or delta t per delta y is going to be decreasing as well. So maybe D and E, because both of those looks like it's decreasing. So let's see which it is. So if we look at our equation sheet and we look at the equation for the Nusselt number, it's our dimensionless heat transfer coefficient, which is proportional to your convective heat coefficient H, you could see that as the position X is increased, um, your H value will decrease. And not only that, we see that that H is a function of the inverse of the square root of X. And so if we graph that, we could see that looks a lot like D. So option E isn't correct because H is not going to go to 0 as long as we have a temperature difference between extreme infinity and then the surface temperature TS. Right, so question 16 is really similar to question 15, but now we're looking at the average convection coefficient, heat coefficient H. So it's the same Same reasoning. So if you look at that average Nusselt number equation, we can see a similar in question. So the correct answer. Question 17. Now we're looking at hydrodynamic length. So we're into pipe flow questions. See that we're looking at that velocity or the average velocity that's in as that flow first enters the pipe. So let's make it just really simple. So if we take a slice of that entrance region and we apply a mass balance to it, you can see if it's steady state, which all these problems are, the mass flow rate in and out are going to be exactly the same. And if we define that mass flow rate in terms of velocity, you could see the density and the area are going to be constant, right? If it's an density is going to be constant, so your velocity or your average velocity will be the same as well, regardless of whether it's in that developing. So question 18, this problem looks at how that hydrodynamic entrance length is dependent on the Reynolds number. And so you can see in both laminar and turbulent flow, that length is going to says your Reynolds number is. All right, question 19, the correct statement about the effect of an increase in the Reynolds number for water flow in a circular tube. So we're looking at the equation sheet and see that at some critical Reynolds number, in this case for internal, it's 2300, you're going to transition to laminar or transition from laminar to turbulent. So, question 20. So here we're looking at how the mean or the average temperature changes as we flow through a heated pipe at a constant temperature. And you can, so this is a constant surface temperature case for internal flow. And you can see from that equation that in this case, that mean temperature dependence on X is an exponential one. So C is the only profile that fits that guy. Question 21 and the last question, at the relationship between the mean fluid temperature and the surface temperature of pipe flow. And if you remember Newton's law of cooling, it's written there up there at the top. And then also you can see in figure 5 that local heat H decreases in that thermal developing. And if we look at that developing, see, and I've highlighted that in yellow there, we can see that as that local heat coefficient decreases, that delta T is also increasing, and that keeps that heat flux constant. So, and then once we've moved into that developed region, right of that highlighted region, you can see that the delta T is constant. And looking at figure 8.5, you can also see that the H value, the local H value, will also be constant. So this gives us a constant heat flux. All right, hope that was helpful. Let me know if you have questions.